Right, welcome to the next session on aircraft drag, primarily focusing on the drag polar. Um, quick little introduction to basically one of the key concepts of aircraft performance, which is the drag polar. It will come in a lot of calculations going forward. It's a prime design design feature that you try and obtain, and as you'll see, there's some key performance characteristics linked to the two values of the drag polar as well. Right. What I'm going to do to begin with is introduce the key concepts of aircraft forces, hopefully a very fundamental concept we've seen before we move into the drag polar itself. So we then need to have a basic idea, a basic understanding of the different types of drag an aircraft can have and how these interact with one another and what produces it. Right. Any aircraft has four key forces. We've got the lift, the drag, the thrust, and the weight. Right, start with the lift. The lift will always act perpendicular or 90 degrees to the relative airflow. So it's a bit of a misconception that lift is what will always produce an upwards force. Sometimes the aircraft might be in a maneuver, hence the lift is producing a slightly different vector. If you find the aircraft in a vertical loop, which we'll discuss later on in a separate video, the lifts may actually contribute to the weight when it's in a vertical loop. Right, 90 degrees to the lift is the drag. So because the lift was perpendicular to the airflow, the drag force is parallel and obviously 90 degrees to the lift. The other two forces involved are the thrust, typically equal and opposite to the drag force in steady level flight in trimmed condition, and the weight, which typically acts vertically down, classes the overall weight points of the aircraft, often seen as the center of gravity. Right, this will become a bit more important when we look at the stability section of this unit. Right, starting with the weight then. This is probably the only major section we'll do on the weight. It's then going to be linked into everything going forward. What contributes to the mass of the aircraft? There's numerous things that you'll see here. So we've got the gross mass, which includes the traffic loads. This is your passengers, your baggage, your cargo. Obviously, depend on the type of aircraft you've got. There's the fuel, separate entity, because you can have the weight of the fuel is the one that majorly changes in flight. So the crew, and then obviously there's the empty weight of the aircraft itself. All right. The center of gravity, which contributes a big aspect of the weight and its location, is allowed to move. It's got an envelope, as we would call it, but it needs to retain within a certain range for the aircraft stability concept. So, as I say, this is going to be something we'll go on to later in the unit, but for now, it can't move, but obviously only within a small range. All right. In steady level flight, this is a typical condition. Steady level unaccelerated flight, often abbreviated to SLUF, SLUF. The lift is equal to the weight, so whatever goes up must be balanced by the forces coming down. Now, one of the things that is important is during the flight, the fuel is slowly getting burned. Obviously, the waste gas is expelled to atmosphere, so that will slowly reduce the weight of the aircraft because of the fuel consumption. This needs to be accounted for. Here's a little scenario to help explain this. What would happen if the aircraft continued to fly at the same indicated airspeed whilst the weight decreased due to fuel consumption? Right, this is going to spoil a little bit of the fun from later on, but to help explain this, we've got the lift equation, which I'll talk about a little bit more later on, is half rho v squared s CL. Right. We've just said in steady level flights, so if it's going to a typical condition for the aircraft is it doesn't particularly want to start climbing. So the weight of the aircraft is going to be equal to the lift. Now, what it's saying is, in order to maintain an altitude and the same speed, so the velocity cannot change, there's a constant number. What can we do about it? Right, so if the velocity stayed fixed, we slowly burn the fuel, these forces then become in balance, and hence lift force is bigger than the weight, the aircraft would start to climb. Obviously, we don't want that to happen. Erase all of that. Right, so cruise climb would slowly occur. Obviously, there's more lift than weight. We've seen in the lift equation. What can be done about this? Right. Quickly rewrite that. Lift half density, velocity squares, area, coefficient of lift. Right. Remember, velocity is fixed. We don't want to climb, so we're going to maintain the altitude. Because the altitude is fixed, typically the density is going to be constant. And in relatively high speeds, you're not going to go changing the wing area. Right, so in order for the weight to equal the lift, something happens to the CL value. Right, so if that's going down, that has to go down. And the only way you can drop that is to change the CL value. So here's the first scenario. This is linked to the lift discussion very shortly. Angle of attack, lift or the coefficient of lift, typical lift curve slope. You might be flying at a particular angle of attack. Corresponds to a particular CL value for our formula. Right. We need to lower the CL value in order to balance the reduction in weight. So a bit extreme just to show this. We drop the CL to a lower value. You can see that's going to correspond to much lower angle of attack. So our new angle of attack. Now, if we lower the angle of attack of the aircraft, it also often results in an increase in the velocity if we don't do anything. So the pilot has to do two things here: drop the nose of the aircraft to reduce the angle of attack, and pull back on the thrust levers because the velocity otherwise would start to climb due to lower angles involved. So there we are. So if cruise climb is not desired, the angle of attack has to be reduced, but this would increase the speed. You increase the speed, but you don't want that to happen. You want the same indicated airspeed. The thrust needs to be reduced. Obviously, the only way we can do that is through the thrust levers and the fuel supply. All right. A couple of key definitions related to the airspeed itself. So there's 4 of these. Only 2 of them are majorly important for where we're going in this unit. Right, we've got the indicated airspeed. This measures the difference between the dynamic pressure and the static pressure. So the pitot vents, pitot static ports, and the static vents on the airframe measures the dynamic pressure, the speed, and produces barometric condition. And obviously, this is the value often displayed in the cockpit. We've got the calibrated airspeed. This often accounts for instrumentational error, often seen on the electronic display, depending on the aircraft, EFIS, ECAM. And it's often seen on the primary flight display. Not that drastically important for this unit. The next one is, this is the equivalent airspeed. So this is the concept that if the aircraft produces a certain dynamic pressure, what would the airspeed be if we drop that to in the sea level conditions? So this is the concept of flying an aircraft at 30,000 feet, produces dynamic pressure. What would the speed actually be if we drop the density to sea level values? Right, so that's the main one. And for calculations later on, we're going to end up working with the equivalent airspeed. So you can see the main thing that's going to occur here, it's the speed of the aircraft at sea level. So this means in our calculations, the density is going to be sea level values. From the ISA table, 1.225 kilograms per meter cubed, or 0.002873. And that's your imperial, so slugs for feet cubed. Obviously, again, you can just read them from the table if necessary. Right, last one, the true airspeed. This is relative to the atmosphere, so it starts to account for wind speed, disturbances, etc. What is the aircraft actually doing? Not vitally important for what we're going to talk about later on. All right, sticking with the basic concepts. So this is starting to build into the lift equation that we've discussed. Primarily the first part of it. So this is the density aspect. Obviously, density starts to affect the speed that we indicate. The rest of it comes from the concepts of rest of the formula. So starting with the lift. Lift, it's a bit of a argumentative condition, this, but lift is often produced or said to be produced by variable pressure distributions due to the speed changing over an aerofoil from nose to tip, leading edge to trailing edge. So forwards as it goes backwards along the cause. The total pressure distribution will produce something called the center of pressure. That center of pressure will be where the overall lift force is said to act. So here's an error for it. What typically happens is as the airflow comes in, it speeds up over the cambered side, so over the top of the airfoil. And generally what you see is a change in pressure that often looks a little bit like that. Now, this change in pressure, typically negative on top, positive on the bottom, is the lift being produced. So these end up being vectors. You can see it's not a great drawing, but the maximum pressure differential occurs at the maximum thickness point. Talk about that shortly. The slip force keeps going up and up and up and up. We add all of these vectors together, you'll end up getting a center of pressure, which ends up being the overall resultant. Now, center of pressure is affected by the angle of attack. So we can see here along the bottom, angle of attack, start at -4 degrees, increasing in increments up to the stalling angle. In this instance, about 15 degrees. We can see here, as we start at low values, the center of pressure is quite far back, quite near the trailing edge. As we increase the angle of attack, so it becomes more and more positive, the center of pressure starts to move forwards towards the leading edge of this aerofoil, gets somewhere near the stalling angle. It's at its most forward point. starts to go back, hits the stalling angle, and then drastically moves back after that. Right. On the airfoil, I've already mentioned some of these key terms. It's just to be pretty familiar with them. Right. First off, point one is the leading edge of the airfoil. Point two is the opposite point. So this is going to be the trailing edge of the airfoil. Right. If I could do this, I always have a ruler, straight line. Between points one and point two is our chords. That's a straight line drawn from leading edge to the trailing edge. As you can get a very similar one that cuts this airfoil in half. And this dashed line. The concept of this is the distance from this line to the bottom should be equal to that line to the top. So that distance there should be equal to that distance. And this dashed line that you can see is the mean amber line. All right. And as I say, I've already spoiled some of these in what I've said earlier on, but the maximum pressure that you get or pressure differential occurs at the thickest point. So it's roughly where I've drawn this arrow incidentally. So this is the maximum distance from the top of the airfoil to the bottom, often given as part of the Naka number of an airfoil. So that is where the code comes from. So we've got the thickness. And last but not least, this red line is the relative airflow, the RF, the relative airflow, so the velocity of the air coming in. It produces an angle with the solid line, the chord line, often given the symbol alpha, the Greek letter alpha, which is used to represent the angle of tau. Right. Few of the things just worth pointing out. You may or may not need these. This is the side view of an airfoil. So if you chopped it in half, this is what you would see. But if you've done the top-down view, you can get the wing area. Typically the span times the chord. These may be average values. The other key point is you often get an aspect ratio, which is the span squared of the area. All right, moving on. Kind of touched on these equations, just explain where they come from. All right, air travels over an airfoil, you get your pressure distribution, you get a typical shape like that. Thickest points, highest negative pressure or coefficient pressure occurs on the upper surface, it's negative, and highest value or most negative value is at the thickest point. We get stagnation points at the leading edge, a similar one at the trailing edge. The area beneath this ends up being the overall lift being reduced. Right. Additionally, a couple of things we spoke about in order for this pressure differential to occur, we need moving air or fluids. So obviously for aerodynamics, it's typically air. And because it's air, that air will have a density. Gravity decreases with altitude. Spoke about this in the last video. So pressure, density, and temperature. If the temperature is dropping with altitude, roughly 2 degrees every 1,000 feet, the density is obviously going to drop with it. All right. The rest of it, we've seen the lift equation already. It creates the basic aerodynamic force model. So aerodynamic force is a half rho v squared. So this is the dynamic pressure multiplied by the effective area involved. Now, in order to produce an equation, we change the proportional sign. To an equal sign, you've got the half rho v squared s. And you introduce, because we swapped the sign, we introduce the constant of proportionality. Starts off as k, but as we know from what we've seen earlier on, this k basically defines the forces that we're looking at. So it can be CL for the lift, or similarly, as we'll see very shortly, can represent the drag. So we change the aerodynamic force we're looking at to the drag force. Same things are involved. Only the constant this time is CD, the coefficient of drag. Right. What we're doing now is move on to the drag analysis. There's two distinct categories of drag. Zero lift drag, and we've got the lift induced drag. Right, the way this works is zero lift drag, including the name, is often given, if you do it in coefficient form, it can be DO or its coefficient can represent CDO. Zero. Lift induced, coefficient of drag, and often given that the symbol I for induced. Right, and the sum of these two, as you can see here, gives the overall drag coefficient for the drag formula. So there it is, CD. Once you've got those two values, it slots into there. All right, very quickly overview these two. So drag is made up of the zero lift component, which is this work. All right, this is basically everything that is the aircraft's made up of. It's the fact it's got the shape, it interacts with the airflow, it obstructs the airflow, it starts to produce turbulence, energy losses due to change in shapes, etc. And as you can see, if you follow this down, it produces skin drag or form drag. And these are produced by the engine nacelles, the wings, so basically just the general shape of the wing, the general shape of the fuselage, the general shape of the tail section, so the horizontal tail, the vertical tail, the landing gear, if it's non-retractable, any struts that might be used to support the wings and the fuselage. So basically just put everything the aircraft's made up of, all add together so you can analyze the nacelle on its own, add a drag value to the wing, add that to the fuselage, to the tail, to the landing gear, to the struts, anything else you want to analyze. This will start to produce the major component for CDO. The other one, which is lift induced drag, follows this section here, is made up of two key components. Subsonic movement will produce vortex drag. talk about in a second. Once you get towards Mach 0.7, we can start to think about wave drag. So this is the concept of shock waves forming somewhere in and around the aerofoil. Obviously, shock waves, you'll see shortly in another video, will produce an astronomical increase in the drag being produced. So obviously increases the CDI component. All right, so we've seen the drag formula. Quick analysis of the two types. So starting with the lift-induced drag. This is the fact you've got the clues in your name here. You've got moving air. In order for a lift force to be produced, you need to move. Part of the lift formula, you need the velocity. Right? Hence, in order for this one, it's induced because of the lift. It needs movement. Right. This particular one, you'll see all the components of the lift formula here. Its coefficients, the airspeed, so the velocity, the mass of the aircraft, hence being the weight, the aspect ratio, this is the wing area. Right. They're the main components which affect lift-induced drag. We've then got the vortex drag, which is part of the lift-induced as we've seen, and produced by the span-wise flow over a wing. So if you look at a wing, head on, there's your fuselage. Excuse the drawings, I'm not a very good artist, but there's a head-on view of a wing. The air would be coming in through the bores. As it hits the leading edge, you'll see it's obviously going to want to go chordwise, so from the leading edge through the TV screen out to the back. But some of it also goes spanwise. It goes spanwise along the top towards the tip. It hits the tip. It will rotate around along the bottom, spanwise back to the root. Right. This rotation here, as it goes round the airfoil, then produces an interaction. So this is a top-down view, if you imagine. Fuselage section again. So you've got these span-wise flows going that way. Simultaneously, you've got the air coming in, wanting to go chordwise, which means you're going to have a summation of the vectors. It's going to start wanting to travel in this type of direction. Hits the wing tip, if we've seen here. It's going to start to rotate around it. And what generally happens is the rotation around it starts to produce some vortices aft of the aircraft. So a vortex basically is this spiral air that comes off the wingtip, massively disturbs the airflow after it. Right. Lift-induced drag. If you get a high angle of attack, obviously high angle of attack corresponds to a high lift coefficient. You may need low speeds. You will get vortices involved. Right. Just bear with me. To Google. Now, this is an aircraft incident that springs to mind that's associated with vortex drag. Obviously, if you cast your mind back to the date, so November 12th, 2001, it was a month just after 9/11. So obviously everyone's minds first went back to it being another terrorist attack. especially given that it occurred in Queens, a district in New York. So same city, 2 incidents a month apart. But this one had nothing to do with terrorists, thankfully, or unfortunately, because as you can see, there was quite a few fatalities in this. The concept with this one is the aircraft flew into wake turbulence or a vortex from a much larger aircraft. So this particular aircraft flies into some wake turbulence. You can see here, it produces a response from the pilot. So obviously the aircraft would start to shake, rotate, and yaw. And so what the pilot does is puts in some rudder control to correct it. Obviously, it ends up over correcting it. So more rudder control goes in. As the pilot keeps going left, right with the rudder pedals, it keeps increasing the energy in the rudder system and eventually overstresses the vertical stabilizer. So in this particular instance, it was a pilot error, but obviously the fact he flew into wake turbulence demonstrates the seriousness of this. Rudder snaps off, the tail section snaps off. Obviously, you'll see later on exactly why, but it becomes uncontrollable. And unfortunately, this particular incident ends in disaster. Right, so this is the one that springs immediately into mind. As for the other one, unfortunately, it's a bit less glamorous. The zero lift drag, I've already mentioned, is the fact you've got a shape there. So for an aircraft, you have to analyze the individual components. You can get a build-up methods often seen in some analysis, come out with an overall value for the zero lift drag for the object you're looking at. So in this case, the aircraft. And you'll see all this is getting at is the shape we've got produces X amount of resistance. So if you put a flat plate in air, it produces a resistance value. Yeah. Huge amount of turbulence, huge amount of disturbance of the air, huge decreases in energy concept. As we make this more spherical, so we put a ball in an airflow, it actually is half problem. So we get a lot less turbulence. Start to elongate the sphere, much less resistance, so it's dropped by 85%. Stretch it into from the teardrop shape into the common airfoil shape. Obviously, the resistance drops even more. So this is this trying to maintain laminar flow for as long as we can, preventing the transition point from occurring too soon. Right, just to finish this little section off, the zero lift drag, as you can see in this diagram, the bottom right, these streamlines are very smooth. So it delays the transition point, so it might be quite far back. The transition point affects the boundary layer. The smaller you keep the boundary layer, the better. So in laminar airflow, this region, where it starts off at 0 on the surface, increases until it's about 99% of the free stream airflow. So if airflow is going past 10, obviously this final vector here will be 9.9. Right, the smaller you keep the boundary layer, the better. Once it goes past the transition point, this boundary layer goes from being a matter of millimeters in height to a matter of centimeters. So basically, I think it goes about anywhere up to twice the size, maybe 3 times the size. So obviously, The bigger the boundary layer, the more disturbance we're getting to produce our airflow, the less lift we're going to get from our wings, the more drag we're producing. Right. Into the analysis of drag and drag curves and where the drag pole actually comes from. So method number one is you can do the build-up method, as I've mentioned. So you get a series of formula for individual parts of the aircraft, add all the values together, you'll come out with the two big values you need. The alternative methods is practical methods. So you can take an aircraft up to a set altitude, keep the altitude constant. You can then start to produce a drag analysis. Right. Once you're at constant altitude, this means the aircraft isn't climbing. So whatever lift force is being produced must equal the weight. Because obviously if one is imbalanced, it causes the change in altitude. So if the lift's bigger, it starts to climb. If the weight's bigger, it starts to descend. So constant altitude indicates the lift value is the same as the weight. Right. As part of the analysis then, we take the aircraft to our altitude and we measure the thrust from the engines. And we do that when it's not accelerating. If the aircraft isn't accelerating, we can assume here the thrust equals the drag. Right, so basically, this is the standard. Mentioned this before. Steady level. Unaccelerated flight. Often abbreviated to SLUF. So that basically means, in terms of vectors, center of gravity, that value, which is the weight, is equal to the lift. And the couple, basic pair of couples, the thrust value has to be counterbalanced by drag value. Right. What we do then is we trim the aircraft out, take a thrust measurement, change the speed, trim the aircraft out again. So obviously this might require a new angle of attack or adjusting the elevators. Get to a new speed, make sure the aircraft isn't accelerating, and take another set of data. We do this with a series of data points. We can start to analyze what we've got. So what we're going to do is determine the coefficient of drag. So this means it discounts any change in density, and it's just a constant number, whether it's a 0 feet, 10,000 feet, 20,000 feet. It's the whole concept of using coefficients. And the other thing we do is, irrespective of the altitude, we convert the speeds to equivalent airspeed. This means in our calculations, we're going to see very shortly, you're assuming sea level density is used. So rho is going to be 1.225 kilograms per meter cubed. Right. Here's our scenario then. So we took our aircraft to an altitude. Doesn't particularly matter where, as long as it's fixed. We took a thrust value when it's trimmed and not accelerating, and the airspeed this occurred at. You can see we slowed the aircraft down, trimmed it back out, took a new reading, slowed down, a third reading, then fourth, and so on. All right, what I've done is I've took these velocities and converted it to meters per second. Obviously, we're going to need to work in the SI base units for calculations. So speed has to be in meters per second. There's our formula. So basically, it's 0.514444 times 211 will give us our airspeed value. Right. First up, what we need to do is calculate, as here, as you can see, find the values of CL, the coefficient lift, CL squared, so square the value we get in part 1, and then hence the drag values. Right, what I'm going to do is just jump out of this 1 second. Take our values, copy that into the whiteboard. Right, this is so you get the concept of where some of the values are coming from. Right, so remember the 3 things we need to work out. We're going to add 3 headings into this, so 3 extra columns. And I'm copying over the text. So I'll only do the first value, and I'll show you this next cell. So we need to work out CL, CL squared, and CD. Right, starting with CL, we're going to use the lift equation, which states lift is a half to V squared SCL. And because of our heading, I'm going to rearrange it for the coefficient of lift. So CL now reads 2 times the lift over the density, the velocity squared in the wing area. Right. Let's get some colors ready. So, based on our theory that we just mentioned, CL, rather than using the lift, it's steady level flight. So the lift is actually equal to the weight. Let's get rid of that. So I'm going to color coordinate this. The weight is a substitution. The density is going to be fixed. Now, the other color I'm going to use here is the values which change in our formula. So as we work our way down, it's going to be the velocity that changes based on each value. And then the wing area is going to be a constant as well. So is what you'll find for the first value here, it's going to be 2 times the weight, which is the mass, times the gravity. So it's metric, so it's 9.81. The density, it's equivalent airspeed, which brings us back down to sea level conditions. Our first velocity is 108.5. That's going to be all squared. And then the area, if you can see behind what I've drawn on, is 25.085. Right, that comes out 0.3666, which will give me our first value for the CL. And then to get CL squared, all I'm going to do is take this value here and square it. So CL squared ends up being 0.1344. Right, so that will be our first value for CL squared. Right. CD done in very much the same fashion. Use the drag formula, except it's going to be CD, and rather than it would be 2D V squared S. Right. In this particular formula, two things will be changing in each line. The drag force is equal to the thrust. The density will be fixed. The wing area is going to be fixed, but the velocity will change in each line. So obviously, as you work your way down, you'll be using that value with the velocity. In the second row, it's going to be this thrust value with this velocity, and obviously keep on going. So we've got 2 times 9,220, 1.225 times 108.5 all squared times 25.085. Right, obviously, similarly to the lift value, you can get a value of for CD. And that just round this up, this is 0.0519, and hence that's going to give us our first value there. Right. What you need to do is work out CL for each of the data points, CL squared for each of the data points, and CD for the data points. Right, obviously what I'm going to do is cheat a little bit, just for the concept of this. Right, there's our values. We're going to have CL squared, and CD. Right, so basically this is going to be the mathematical form in terms of Excel. So it's going to be equals 2 times. So the values that we're going to be using are the ones that you're seeing in the PowerPoint and the walkthrough there. This is the lift, so it was equating to the mass, which was 6760 times the gravity, 9.81, dividing that by the bottom value, so it was density for the equivalent airspeed, the velocity of the first value, which is the 108.5, that's going to be all squared, and then we're going to times that value by the wing area of 25.085. All right, obviously that corresponds to the value I had in the little walkthrough there. Drag that down, get all our values. CL squared, nice and easy. I'm going to take that one and square it. Drag that one down. So we've got the values. All right, and lastly, CD. Similar to CL, it's going to be top part of the fraction, which is 2 times the thrust. So this value is going to change. And on the bottom, density per sea level. The velocity again, squared, and our ring area again of 25.085. Obviously, you can see that corresponds to the value we had in the walkthrough as well. Right, drag that down. There's our table of results. Now, in the PowerPoint, just to show you where this is going to go, it says use the data. So there's our values if you need them. And I'm going to produce two graphs of one, which is the coefficient of drag against CL. The other one is CD against CL. Right. Graphs. Right. First one on the x-axis is CL. And the y-axis is going to be the CD values. And just put some grid lines, etc. on, neaten this off a bit. Right, so CL on the bottom, CD on top, CD, CL. All right, trend line. If we go on more options, it's best to do a polynomial. Keep increasing the order until it starts to curve off. So power 5, you can see if it goes higher than that, it goes a little bit skewed. So there's our line of best fit, if you like. All right, copy that over. Nice and big so we can see, right. What I want to do is, the first thing I'm going to do is add a line. It starts at the origin. I don't know whether it's going to work on there, but we'll give it a go. It should be a tangent to the curve. Like that. Just change the color so we can see it. Right. Tangent to the curve, it's very straight. Track that so it's through the origin, as you can see. All right. Concept of this one is once you've drawn a tangent from 0, 0 to the first point it touches, you don't need to touch the curve once. What you need to do is take the gradients of this straight line that we've just added. So back into our pens. Right. It's obviously a bit difficult because I'm reading this on the computer, but the concept here is picking 2 points we can easily read. So there's point number 1. You can see that's intercepting roughly 0.04, 0.4. And the second point has got to be this one, nice and easy, because it's the origin. We know that should be 0, 0. All right. Calculation wise, for this gradient, the gradients, y2 minus y1, x2 minus x1. Right, on point 2, both the y values and the x values is 0. y1 is 0.4. That's reading off the y-axis. And reading off the x-axis is 0.4. Right, if you stick that in a calculator, we should come out with 1/10. Right, obviously, what does that mean to it? So think what we've just done. We've took the y-axis, which is labeled as CD. We took the x-axis, labeled as CL, and we divided one by the other. Right, so as it is, this is the drag to lift ratio. It's saying it's 0.1 or 110. Typically, we don't really work in drag to lift ratio, we work in lift to drag ratio. So the final step here is, can we invert this formula? So I'm going to flip this part. So it becomes 10/1. And flip the other part. So it's a CL over CD. So first key aerodynamic feature for our aircrafts is the lift to drag ratio for this particular one is 10 or 10/1. Obviously, the higher you get this number, the better, because it's become more aerodynamically efficient. Right, that quickly covers graph number 1, a method to work that out. Graph number 2, I can jump back into Excel. Nice and easy to do this. If you want to cheat, copy, paste that. The y-axis stays the CD, but the second graph now plots the coefficient of lift squared. Let's me do that. So select our data, edit. It's the x-axis that's changing. Sales squared. Quickly change this. This is going to be the linear drag pole I'm producing. Which obviously means on the bottom that's now our 2. And the final bit to modify is the trend line. Get rid of the polynomial one. We trend line for this one is linear. I'm just going to put it backwards a little bit to that, but make sure the axis starts at 0. This is just so you can see what's going on. Right, copy that into here. So graph number 2 this time. It's all done for us, this bit. So by doing the line of best fit, the linear line of best fits, just makes it a little bit easier for me to, rather than have to do it manually. Right, again, it's a straight line. So this now goes through the theory of a straight line. General equation says y equals mx plus c. Right. First thing I'm going to do before I even look at anything else is find out what m is, the gradient. Again, standard formula. Right, this is a little bit harder. It's not a great graph to use. And zoom right in. This is going to be very approximate. There's point number 1. And I take that as point number 2. Right, so y2, that is 0.12. These are then going in 4s. There's 0.014, 12. So this is 0.132. The x value, reading downwards, is 1.4. We're then going to subtract our 0.1 value, so it's minus the 0.1s. A little bit harder this time. That's 848892. So 0.092 for the y. And for the x, if you read down, that's 0.8. So this is very approximate, as I say. It's not pretty obvious or very easy to read this graph on a computer. But I'm hoping you get the gist of where this is going. Right, work out the gradients. So in the calculator, that goes right. That very approximately is 115, which on the SD button 0.0667. Right, that is value number 1 that I can slot in for M. Value number 2 is the y-axis intercepts, and if you look very closely at the graph, it's not quite 0.04, it's just below it. No, there's 0.036, so it must be higher than that, but less than 0.04. So what I'm going to say here, just for argument's sake, is 0.039. Right. Let's insert these numbers into the straight line equation, y equals mx plus c. So far, we've got y equals 0.0667x plus 0.039. Now, y and x is not the y-axis, it's not the x-axis, it's what we've actually labelled them. On the y-axis, we've labelled CD. And on the x-axis, we've labelled that actually as CL squared. Right, this is going to be jumping a little bit now. So there's our equation. CD equals 0.0667 CL squared plus 0.039. Very quickly check how we've got on. Trend line. Now display the equation chart, and you can see that's actually very, very good guess. We've got 0.066 and 0.0392. So very happy with the numbers we're working with. Guys, if you think about what we've done, we've got two values. This is the easiest one to talk about. Best. On the x-axis, it's gone from, you've read the y-axis intercept, and at that intercept, our y value happens to be 0. Right. Its clues are in the name here. It's 0 lift drag. So this is the point or the amount of drag being produced because there's no lift being involved. So it is just the shape aspect. And you can probably guess that because the coefficient lift's involved in the other one, this section is CDI, or the lift induced drag. Right. And finally, it's usually written the other way around. It's usually written CD equals CDO plus K CL squared or CDO plus CDI. Right, so this particular drag polar that we've analysed should read 0.039, so the zero lift drag component. K is the other number. CL squared, right. So just put all this in a nutshell. CDO, that value is K, but all of this section, as you can see, is CDI. Right. The final words on these numbers. This is for the Jetstream 31 aircrafts. So the real life scenario, it's a real life application. And I'm going to come back to these values at the very, very end to do a final quick analysis with. Right, so remember, the drag polar number plus a number CL squared, and it's always CDO on its own, K with the CL squared component. Right, so this very quickly recaps. Right, in approximate methods, might want to mention this, in approximate method, K, this is the CDI, and K can often be worked out or approximated by going 1 over pi. E is not Euler's number or the exponent that you're often familiar with on calculators. It's the Oswald efficiency value, which I'll show you in a second. And then you're going to multiply that by the aspect ratio and then times it all by CL squared. Right, so K is 1 divided by, on the bottom, pi, Oswald efficiency value, the aspect ratio. Right, and the Oswald efficiency depends on the wing sweep. So a quick approximate method here. Right, you can only really use these if the aspect ratio is bigger than 6. Very typical for most wings anyway. Well worth mentioning. Now, once you've got the drag polar, so once we've got CD equals C0 plus KCL squared, we can then move into producing drag curves. All right, drag curve. What we see here is all three components together. So if we go back to the start of all of this, we've said CD, or the overall drag, lift induced, sorry, CO lift plus lift induced. Right, so here we are, lift induced drag. Decreases as you speed up. It's the inverse of CL squared. The parasitic drag or the zero lift drag increases with velocity. So the faster you go, the more you increase that component. Right. One particular point to start off with then. So I've quickly sketched over these two components. At one particular point, they intersect with each other. And if you look when you add these together, so this is CDO plus CDI uses the total drag curve. It's adding the two readings together to give us a total. When you find the point of intersection, it incidentally corresponds to the minimum point. Right. At the minimum drag, we can say zero lift drag is equal to lift induced. Based on our definitions, CDI equals KCL squared. Right. So at minimum drag, we can rearrange this relationship because it's both equal to each other and rearrange it for CL. And that's very quickly CDO, you can divide through by K, leaving it with the CL squared on its own. We're going to square root that. And that's going to give us our coefficient lift at minimum drag. Right. In terms of what we've done then, for the jet string, going back to our example, coefficient lifts at minimum drag, CDO over K. That's going to be 0.039 over 0.0667. Right, so you can get your CL or key aerodynamic feature at minimum drag, very important point for aircraft operation. In this case, that's going to be 765. Right, and in terms to get the other corresponding point, CD, you've got two options here. You can stick your CL value back into the drag polar now. You now know that value. You can get CD out. Alternatively, you can just simply multiply this value twice. And that is because at the minimum drag, CDO is equal to CDI. So whatever that value is, happens to be that. And you already know what that is. When we said earlier on, CD is CDO plus CDI. So if that number is the same as that one, you can do it twice to get CD. All right, so it just saves you 3 at a time. It's not essential. You've got two methods, both give you the same answer. All right, a couple of things to finish this off. Second important bit is the minimum power speed, often associated with the endurance of a flight. You try and operate minimum power, you get a separate CL component. This just involves multiplying CDO by 3. All right, finally, if we just jump back 1 second, Right, we've done the drag to lift curve. So obviously we inverted this and got it was 0.1. There's an approximate method, so you might not be able to obviously plot graphs quickly. This might be a bit of a pain method. An alternative one for you. Just get a new whiteboard to start this from scratch. Right. At minimum drag, this is a key feature. Oh, don't want that bold. Right, here we go again. Try again. At minimum drag, you are typically operating at lift to drag maximum relationship. Right. It's pretty obvious what this is going to be. So lifts half rho v squared SCL. You can divide that by the drag. It's a lift divided by drag ratio. Divide all of that by the drag formula. Half rho v squared SCD. Half is a half. You're going to be flying the same altitude at the same speed, and it's going to be the same aircraft. So basically, the lift to drag ratio is the same as CL over CD ratio. Right. This is going to be a starting point for where I want to go, really. On top, we've got the coefficient of lift. On the bottom, we've got the CD value. And we've just said earlier on that CD is actually the drag polar. So CDO plus CL squared. Right. Starting off with the conditions then. So based on what we've just been through, a couple of things to bear in mind. Do these in a different color just so they don't get mixed up. At this condition, CD is equal to 2 CDO. So this is the idea that both the zero lift drag and lift induced drag are equal to each other. Part of the drag polar equation, you want to split CDO because it equals to CDI. That can be rewritten as KCL squared. And I've also pointed out that at minimum drag, the coefficient of lift is CDO over K all square rooters. Right. Substitution number 1. CL. There's our CL. On top of this fraction, I'm now going to go and substitute the coefficient of lift minimum drag. So on top, this will now say CDO over K. All square rooted. So that's substituting into there. Right. And on the bottom, KCL squared is CDO. And we've also got CDO there. So it's CDO plus an alternative CDO. So we've got two lots of it. The alternative way of writing the drag polar, this can become 2 CDO. what we've got is square root divided by a nice value of 2 CDO. So what I'm going to do is just write this linearly so it's a little bit easier to see. You've got CDO over K. That's technically over 1. You're dividing it by 2 CDO. That's also over 1. It's pretty straightforward in terms of writing this section. When you divide, we invert that to a multiplication sign and invert this. So all I'm trying to do, the way I'm writing this is just separating them out rather than having a fraction, if you know what I mean. So we've got one term, which is going to be CDO over K. That's divided by 1. That now becomes multiplication of 1 and 2 CDO. Right. Just to keep us on track, all of that now equals an alternative way of saying CL over CD max. So rather than just doing the lift to drag ratio, we've got the condition for CL. We've got a special condition for CD. I've written them as a linear relationship, just so it's a bit easier to see what's going on. So if you want to neaten this off, you're going to have 1 over 2 CDO. Is this bit, and that's going to be multiplying CDO over K. Right. We'll ignore this middle bit, just write this out so you can see what we've got. CL over CD max equals 1 over 2 CDO CD over K square root. Right. Step number 1, from this point, we're going to square both sides. So we're getting end up with the square of the drag ratio, the square of that. Right, on the right hand side, if we're squaring, just to neaten this off, 1 squared obviously stays as 1. 2 squares turns that to 4. CDO then gets all squared as well. And next to that, we're squaring the square root, which gets rid of it. Right, what we've got left is CDO on top. We could cancel out one of the powers. Right, so if you're rewriting this, we've got 1 over 4 CDO times K. That's still equal to the square of the lift to drag ratio. Right, the final step, it's a bit reverse this, but although we've squared it, we've neaten this off without going to square root it. Square root of that brings us back to lift to drag ratio. But I'm square rooting the other side as well. Right, and finally, the square root of a quarter. So this is the 1/4 that's inside this. If you try this and calculate, you're unsure, but if you square root a quarter, it ends up as a half. This can come out, so the square root of a quarter is actually just 1/2 multiplying the square root of 1/CDO times square. Right. This is an alternative formula or a theoretical formula for the lift drag ratio. And just to show you how this relates to our previous example, the jet stream, CDO was 0.039. Here was the 0.06667. Right, this is just to see how things correspond. Right, so lift to drag ratio for the maximum should equal 1/2 times square root of 1/0.039 times 0.06667. All right, so in the calculator, 1/2 times that'll come up 0.981. Right, so you can see where I had 10 in the graphical example. This one gives us a slightly lower number. It's the theoretical methods. Obviously, it'll be practical errors in the other one, hence a slight tolerance difference, but it virtually shows you that you can get very close or very similar output to practical analysis. And so there we are. That is the alternative method. So at the minimum drag speed, you will also have your lift to drag ratio at its maximum, and that corresponds to CL at minimum drag and CD equaling to CDO. All right, and that brings us to the end.